In the previous unit, we discussed about axial loading, and we also said that before getting into the twisting and the bending, we will talk about stress in a more detailed manner. Okay, so and then this is necessary because in torsion or the twisting and in bending, different kinds of loading conditions will come and they will result in different kinds of stress fields, and to understand them we should have a clear idea about what do we mean by the general state of stress at a point under a very general kind of loading condition. So this full unit will be about this, the stresses, and how to look at them from different coordinate system and all those things. To start with, first let's define what the general state of stress at a point is. For that, what we need to do is, say we have say a body, very general body, which is subjected to maybe various forces and moments. So this is, say, a force F1, which is, say, this is a force coming from behind, say F2, and maybe this is a moment, and like that. Okay, some other force may be coming like that, F3, whatever, maybe one. Okay, say this is C1 and this is C2, etc. And this is a 3D body. Let me try to some representation of this 3D body. Sorry, maybe something like that. Okay, so this is a 3D body on which various forces are acting. And let me also draw the axis, maybe so somewhere like that. Okay, so somewhere here. Okay, so this is X, so this is Y, and this is Z. Okay, now now when this general body is subjected to these many forces and couple moments, and we are looking at say a point here somewhere inside the body, say the point P, and we are asking what is the stress at that point. Now first we have to define what exactly do we mean by this question. Okay, what is the meaning of when we say the stress at P? Because earlier till now we have seen that, okay, there was a rod, we are pulling, so what was the stress on that plane, so force over area, like that. But now we can't say anything because the things are so complex, right? So now we have to define it more systematically for this general situation, so that we can say something quantitatively very meaningfully. Okay, for that what is generally done is we take maybe yellow color. Through that point P, let's pass a plane perpendicular to YZ axis. Okay, through P, let's cut this body by a something like that. Okay, so this plane is parallel to YZ plane, and we have cut the body into two halves now. Okay, now so let me try to draw something. I can only try. Okay, so here, and this cut portion is somewhat like this, isn't it? So this is a bad drawing. So in a way, so what I mean is this is parallel to the YZ plane. Okay. So now this was okay, X, Y and Z. Now P is now visible. Okay, so now P is somewhere here and it's visible. So what we will do, and because these forces are now not in the picture, the other forces are, okay, so this F1 is here, this C2 is here, anything else, F3 is also here, all those things are there, okay, but F2 and C1 are not there because we have thrown away that right hand side part, but then their effect must be taken into account here, right? To draw this free body diagram, we should show the effect of those forces. That means earlier those forces in some way were affecting this section, okay, and that is why it was in balance. So now here, if we now try to draw the forces, they will never, obviously intuitively they will not be uniform. At every location some other force would be acting. Now, so try to imagine that there is a small area dA or delta A. You take a small area delta A around that point P, okay, and try to see or imagine the force which was acting because of all this thing. Maybe it's called, say, F, and okay, that's fine. So this was the general, some arbitrary direction this force was acting at that particular location. If you now consider some other area, this will be completely different force. Maybe here if I take an area, the force could be in this direction, okay. Now at this location, so every point will have different forces. So we are considering at that particular location in a very small area around P. Now suppose that force is F. What we can do is we can split that force into two components now. One perpendicular to this area, okay. So let me draw that first, say, now that force is, say, I'll call Fx, okay. Now the other component, we will resolve this into one, the other one in plane of that dA, okay. Now let that be shown as, say, here. So this was maybe F parallel, I'll call F parallel to the plane. So this is perpendicular to the plane, and this perpendicular is known to be the x-axis because this we had cut parallel to the YZ. So the normal to any area element will be parallel to x-axis. So this is in x direction, but this we do not know where it will lie because this completely depends on the direction of the F in general 3D space, okay. Now this F parallel now can be split into two components, which can be drawn as maybe, so this is F, or I'll write V, that's the general practice. So this one is a V, and then all these forces are small, so why don't I write delta everywhere, okay. So this also is delta, this also is delta, and maybe this also is delta F only, okay. So and then this also is delta, fine. Now this is delta V, but I have to tell some directions also, right? Now this has come from resolving one component in x direction. So first thing is that I'll put that x here, and then I am resolving this F parallel into y direction. Similarly, I can get the other component of this to be this, which will be delta V again this superscript x is saying that the area's normal is in the x direction, and this I'm resolving in, sorry, not in y but in z, in the z direction. Okay, so that's how we have resolved all these forces, and now we are in a position to define the stresses on this elemental area. Now what we will tell, we will say that, okay, now sigma x is equal to limit delta fx by delta a. Because this f, I am writing sigma here because it's like a normal stress. See, this f, delta fx is perpendicular to this area delta a, so that's why I am writing sigma, because it's a normal type of stress. And then for these two I'll use say tau, and because there are two symbols, I'll write this perpendicular, the normal's direction first, say x, and the resolved direction to be y should be equal to limit delta vxy by delta a. In fact, on delta a also I can write say x here, this I can write x here, okay, and all these things, limits are taken when delta a tending to 0. I am not writing them, it will be very clumsy. And similarly tau, this one will be tau xz, sorry, tau xz will be limit delta vz over delta ax. Okay, so that's how we have defined three terms. And because see, these two are having these two subscripts, so it's always good and to have here also two subscripts like sigma xx, tau xy and tau xz. And first subscript everywhere is telling that this area element which we have chosen, its normal is in this direction, x direction, and the second subscript is telling us that we have resolved that in which direction, okay, x, y and z. So that's how we define them. Now this we did by cutting a plane which is parallel to YZ plane, okay. The same thing you could have done by taking a plane say parallel to XY plane, right? So here maybe you could have taken a plane which is say parallel to XY, okay. Then you would have got similar area element whose normal will be in z direction, okay. So then we could have written three components there itself, okay, like this. So sigma tau, the first component should be the subscripts, first part will be the direction in which the area has the normal, okay. So this is z and z, and the second component will be z, because sigma is normal, so the force should be resolved in that, and this is sigma tau zx and tau zy. So like that you should define. And again the third one is you cut a plane parallel to the xz plane, okay. So this was xy, fine. So xz plane, so that you will get normal in the direction of y, so you will get another three things like sigma y, and here it's y, x and z. So these are the 9 numbers which if you specify, then you can say that I know the state of stress at that point P, because all these things are evaluated in limit when delta A tends to 0. So basically what you are doing is you are squeezing that area so that you can approaching the point P, okay. So these things generally are not written or demonstrated like this, it is explained in this way, but they are represented in a very systematic way in this form. So what generally is done is you draw a cube, okay, like this. Okay, on this cube you draw the stresses. Let me draw first. Suppose this is x direction, x, y and z. Fine. So then this direction is sigma xx, this direction is sigma yy, and this direction is sigma zz. Okay, and now coming to say the taus, the shear stresses on this direction. See, you come here. Now here so if you see this one, tau xy was on this direction, right? And similarly, okay, so here you have this and this. So this is tau xy. What does it tell you? Now the first subscript is telling you that the area which you are considering, it is having a normal in the x direction, and you have its so the normal is in the x direction and the resolved component of the force was in the y direction. So that gives you this, and similarly this will be also tau y x. Okay, and then is it fine? Because this area, I think, this is parallel to yz, so I think, yeah, so that should have been different. So here the area is perpendicular to y, so this is tau y x and this is tau xy. Fine. And similarly here the area is perpendicular is in the y direction, so tau y component is in the z direction, and here it's tau perpendicular is in the z direction and component in y, and here it's tau perpendicular z in x, and one more in this, that tau perpendicular in x component in z, right? So that is how you generally represent all the states of stress. But then whenever you look at this cube, you should think that there is a point here somewhere at the center. Okay, so your main concern is about that point, not this cube. This cube you have imagined so that you can define planes. Okay, 3 independent planes which you can define, and then always you have to shrink this cube to the point P, and then you say that all these stresses are at that point. And corresponding to all this, you will have the other side stresses. I'll not draw them here, okay, but exactly the same thing will be there on the other side. And these 9 numbers, they are generally written in this form. Okay, so like sigma xx, sigma yy and sigma zz, and then you have tau xy, tau xz, then tau yx, tau yz, tau zx, and tau zy. Okay. Now, as we had discussed in the previous unit, the last section, if you see this, so now you are in a situation to where you should be able to visualize what stresses are causing what strain. Okay, so this tau yx and tau xy are actually causing this gamma xy thing. Now the point what I'm trying to make now is, see, if you look at this cube from, say, this side, okay, and assume that all these other faces are not having any stresses, okay, and now what you will see is a square on which stresses are acting like this, right? So this is tau yx, tau xy, tau xy, and tau yx. Okay, they must be same and opposite direction because they are not at two different planes. They are actually at the same point because you will shrink it, but to draw this plane you actually have to draw the free body of the right hand side by removing the left. So you will see an exact opposite direction stress here. Now if you write, suppose you take a square of length or uniform area A on all sides, you can write the couple moment equation, and from there it will be clear that this tau xy must be equal to tau yx. Okay, because if this distance is A, so tau xy times, say, the area is unity on, okay, so all these areas are unit 1, then tau xy times A must be equal to tau yx times A. Okay, so from that A will cancel out, so tau yx equal to tau xy. So that you can do for all the combinations, and from that the conclusion is these any six, or the upper six or the lower ones, you can choose. These 6 numbers will uniquely define the state of stress at a given point. Okay, now these numbers, once you know this, you know this. If you know this, you know this, because they are symmetric. Okay, so this is what is called the stress tensor of that point. So these 6 number, if you know, you should tell that, okay, I know the state of stress at a given point. But then the question comes, if we change the orientation of these xyz things, okay, because we have chosen a particular plane or axis, set of axes, and then inside that we are talking about all these planes and the values. But then if we change that, then obviously the stress is not going to change because it's a physical parameter, but these numbers definitely would change, right? But so that's what I was telling, that the tensor as a parameter, I mean that physical property, that stress as a tensor, that doesn't change, it remains as it is. Its components, so these are the component. Even never think that this matrix is the tensor. This is the matrix representation of the tensor, which is the stress, which is an invariant. Okay, so the stress doesn't change if you change the coordinate system. Okay, a tensor is invariant under coordinate system transformation, rotation. Now but the components will change. Okay, now how they will change in a particular condition and why are they important, so that will be the topic of discussion in the next segment. So see you in the next segment.